Hey everyone, welcome back to The Explainer. I am seriously so excited for our journey today. We're going to embark on a truly spectacular cosmic zoom. We are starting right here, with our feet firmly planted on our home planet, and we're going to zoom out, scale by scale, all the way to the very origins of the cosmos. Now I know it's a massive topic, but as always, we've broken the whole shebang down into clear, visual steps. Okay, here's our flight plan. 1. Earth and the Moon. 2. Inside our solar system. 3. The life cycle of stars. 4. Galaxies in the universe. And finally, 5. The Big Bang evidence. Let's just dive right in.
Section 1. Earth and the Moon.
So, we begin our zoom right here in our own local neighborhood. It's really easy to take the sky above us for granted, but everything we see is a product of these massive objects in motion. Take the moon, for instance. It orbits us at an average distance of about 400,000 kilometers. But it's absolutely crucial to remember that it doesn't actually produce its own light, right? The moon is only visible to us because it acts like a giant mirror reflecting sunlight. As it travels in its roughly circular orbit around Earth every month, the sun illuminates different portions of it from our perspective. And that's exactly what gives us the phases of the moon, from a thin new crescent to a big full circle and back again.
And back down here on Earth, our everyday lives are totally governed by mechanics. Our experience of light, dark, and the changing seasons, they all boil down to just 3 simple motions. First, the Earth spins on its axis once every 24 hours, giving us our day and night. Second, it takes roughly 365 days to complete a nearly circular orbit around the massive gravitational pull of the sun. And third, and this one is a real game changer, our planet is tilted at an angle of 23.5 degrees. It's this exact tilt that causes the changing seasons. So when your hemisphere is tilted toward the sun, you get those longer, warmer days. Hello, summer!
Now, to understand how fast the moon or our planet is actually moving, we use this really elegant equation. Average orbital speed, which we call v, is just the total distance of the circular orbit. So that's 2 times pi times the radius r, divided by t, which is the orbital duration, or the time it takes to complete one full revolution. It's literally just a simple application of speed equals distance over time, but, perfectly scaled for the cosmos.
Moving on to Section 2, inside our solar system.
So, every planet, asteroid, and comet in our neighborhood is bound by the massive gravitational attraction of the sun. And get this, the sun actually contains more than 99% of the entire solar system's mass. Crazy, right? But the remaining matter formed into 2 very, very different types of planets. Notice the stark contrast here. The 4 inner planets, Mercury, Venus, Earth, and Mars, they formed in the hotter regions near the sun. So they're small, dense, and rocky. Simply because only materials with really high melting temperatures, like metals and silicates, could actually remain solid there. But further out, in the cooler regions, light molecules like water and methane could freeze into ice. This allowed the outer planets, Jupiter, Saturn, Uranus, and Neptune, to grow incredibly massive, eventually capturing light gases like hydrogen and helium. So they ended up massive, cold, gaseous, and boasting a whole bunch of moons.
Just look at the sheer scale of these outer planets. What you're seeing here is Jupiter, by far the largest planet we've got. See that massive swirling storm? That's the Great Red Spot. It is so enormous and resilient that it has literally been raging and visible from Earth for over 200 years. Jupiter's incredible gravity allows it to hold on to this turbulent, thick atmosphere of hydrogen, helium, ammonia, and methane. And a bit further out, we hit Saturn. Captured here by the Voyager 1 probe, just check out those spectacular rings made of ice particles. It perfectly demonstrates the kind of incredible icy debris that gets captured by the intense gravitational field of the gas giants. It's a freezing, turbulent world, radically different from the solid, rocky ground we're standing on right now.
All right, Section 3, the life cycle of stars.
Zooming way, way past our sun's gravity, we enter the absolute vastness of interstellar space. And out here we discover that stars are not permanent fixtures at all. They're actually born, they live, and they die. A star begins when an interstellar cloud of dust and hydrogen gas basically collapses under its own gravitational attraction, forming this heating protostar. When the core gets hot enough, boom, nuclear fusion ignites. Hydrogen fuses into helium, releasing immense, intense energy. For billions of years, the star hangs out in a stable state. It's like a cosmic tug-of-war, where the inward pull of gravity is perfectly balanced by the outward thermal pressure from fusion. But eventually that hydrogen fuel runs out. Gravity takes the wheel, the core collapses, and heats up even more, while the outer layers expand massively, turning the star into a red giant to be exact.
So what happens next? Well, the ultimate fate of that red giant depends entirely on its mass. It's really a tale of two extremes. Low-mass stars, kind of like our sun, will eventually just shed their outer layers, leaving behind this tiny, incredibly dense, super-hot core called a white dwarf. And over billions of years, that'll slowly cool into a dark, dead black dwarf. But high-mass stars, they burn fast and they die hard. They fuse heavier and heavier elements until their core collapses catastrophically, triggering a violently explosive supernova. What's left behind is either a rapidly spinning neutron star or, if the star was massive enough to begin with, a black hole, an object with gravity so intense that literally not even light can escape its grasp.
Look closely right at the center of this glowing shell. See that dot? That is the dense, cooling white dwarf. This is what the peaceful end of a low-mass star looks like. That beautiful glowing shell of ionized gas was expelled by the dying star, forming what astronomers call a planetary nebula. Now, this phase is relatively brief. We're talking only about 10,000 years, which is a blink of an eye in cosmic terms, but it's absolutely crucial for distributing new, complex elements back out into space.
Now, on the total opposite end of the spectrum, we have this. You are looking at the Crab Nebula. These are the beautifully chaotic, scattered remains of a massive supernova explosion. And get this, the explosion that created this nebula was so incredibly bright that it was actually recorded by Chinese astronomers here on Earth almost 1,000 years ago, back in the year 1054. In violent explosions like this, the temperatures get so unfathomably hot that elements heavier than iron are forged and just blasted out into the universe.
Section 4. Galaxies in the Universe.
So stars don't just wander around out there alone. They actually cluster together by the billions to form these massive swirling structures called galaxies. When we look up at the night sky on a really dark night, we see this milky band of light, right? Well, that is actually the edge-on view of our very own Milky Way, a spiral galaxy packed with over 800 billion stars. The image on the right, which was taken in infrared from a space probe, reveals the super dense central bulge of our galaxy. Since our solar system sits way out near the outer edge of this massive spiral, we're basically looking inward, right through the disk.
Now, because space is so mind-bogglingly vast, measuring distances in kilometers becomes completely useless pretty quickly. Instead, astronomers use the light year. That's the distance light travels in a vacuum in one single year, which works out to nearly 10 million kilometers. The Milky Way galaxy alone is around 100,000 light-years in diameter. To put that into perspective, it means the starlight you see when you look up tonight is actually ancient history. The light from even our nearest neighboring star, Alpha Centauri, took over 4 years just to travel to your eyes.
But as astronomers started looking at incredibly distant galaxies, they noticed something really peculiar. When they analyzed the light emitted by glowing hydrogen in those far-off galaxies, they found a shift. Which leads us to a massive, mind-bending question. If the universe is just sitting there, filled with glowing stars, why does the light from these distant galaxies look stretched out and noticeably redder than it should be?
Which brings us to Section 5, the Big Bang evidence.
Well, that simple question, it's actually the key to unlocking the greatest mystery of the cosmos. To answer it, we have to look at the ultimate origins of literally everything. The answer lies in the Doppler effect. Think about an ambulance siren. You know how it drops in pitch as it drives away from you because the sound waves are stretching out? The exact same thing happens with light. When a galaxy is moving away from us, its light waves stretch into longer, redder wavelengths. Astronomers observe that almost all distant galaxies show this redshift, and the further away they are, the greater the redshift is. This proves, without a doubt, that galaxies are rushing away from us at tremendous speeds. The universe is expanding.
Okay, this next part is truly mind-blowing. If everything is expanding outwards today, it means in the past everything must have been closer together, right? What you are looking at here is literally the echo of the Big Bang itself. This is the cosmic microwave background radiation mapped by the Planck telescope. It's the residual heat from the initial massive explosion of the universe. Because the universe has been expanding for so long, this ancient, incredibly hot radiation has been stretched and redshifted all the way down into the invisible microwave spectrum. And it is absolutely everywhere we look in the sky.
Back in the 1920s, the brilliant astronomer Edwin Hubble found a mathematical relationship here.
By measuring exactly how fast galaxies are receding relative to their distance from us, he formulated what we now call the Hubble constant. It's a neat little equation where the velocity of recession equals the Hubble constant multiplied by the distance. And what that does is it effectively gives us the current expansion rate of the universe.
So why does that matter to us? Because if we have the rate of expansion, we can basically run the clock in reverse. If we run that expansion backward using the inverse of the Hubble constant, we can estimate exactly when all the matter in the universe was packed into a single, incredibly dense starting point. The math tells us that this explosive beginning, the Big Bang, happened roughly 14 billion years ago.
As we wrap up this cosmic zoom, I want to leave you with one final profound thought about the ultimate fate of our expanding universe. Right now, it's expanding, sure, but scientists calculate that about 80% of the material in the universe is currently invisible to us. It's dark matter that doesn't emit any radiation we can see. The ultimate fate of everything relies on this hidden mass. Is there enough hidden gravitational force out there to eventually hit the brakes, halt the expansion, and pull everything back together in a massive big crunch? It's a huge mystery, and one we are still desperately working to solve. So keep looking up, keep asking those big questions, and I'll catch you in the next explainer.